All right, thanks, Randy. As Randy said, I'm Jacob Carlin. I'm a research scientist here at CIMMS NSSL. And today I'll be giving the introduction to the work really being led by Charles Kuster and also Randy Bowers from the National Weather Service Norman office on the use of KDP as a downburst precursor, and specifically a downburst precursor in low shear environments. So, as I'm sure you all know much more intimately and better than I do, the timely prediction of downbursts remains a primary forecast challenge. And with surface stations typically being spaced too far apart to fully resolve most downbursts, radar is going to play your primary role in detecting them. So there's been a number of signatures proposed that have been associated with downbursts. Of course, you have divergence at the surface associated with the downburst itself. This obviously only provides a little bit of lead time because you're measuring the actual downburst as it's occurring, and can suffer from lack of low-level coverage further from the radar site. And you also have mid-level convergence, sort of a mass conservation argument. This has not always been observed when investigated, and so far there hasn't been a clear correlation between the magnitude of the convergence and the subsequent intensity of the downburst. And then probably a really primary signature that is used associated with downburst detection is descending reflectivity cores, which reflects an enhanced flux of precipitation downward below the melting level. Obviously, with all radar-based metrics, the temporal resolution of the radar remains a concern, with some of these signatures evolving on the order of 1 to 2 scans. So with the polarimetric upgrade of the NextRad network, there's been a number of studies that have looked at the polarimetric signatures of downdrafts more generally. So troughs of locally depressed ZDR values have been observed and associated with large tumbling hail in downdrafts, although other studies have actually reported an increase in ZDR in these downdrafts, which they attributed to graupel instead of hail. So there's obviously some variability there. Scharfenberg 2003 looked at enhanced KDP values at the base of these troughs and associated it with melting ice within the downdraft. And then you just have some other more indirect metrics associated with melting hail and graupel, such as reduced correlation coefficient, or associations have been found actually between the strength of ZDR columns as a sort of a metric for how strong an updraft is, and downburst intensity, with the idea being, stronger updrafts can support the generation of more hail and graupel. So to kind of motivate the work that Charles will be presenting today and sort of why we want to be looking at KDP cores for downbursts, I have here the equation just for the acceleration of the vertical velocity in a downburst, as is typically understood. We have the precipitation loading. We have negative thermal buoyancy due to latent cooling and microphysical processes. And then you can have a dynamic pressure perturbation. And for the purposes of today, since we're really concerned about sort of these pop-up low shear environments, we'll be neglecting the dynamic pressure perturbation. So why we're interested in KDP? Well, the KDP of dry hail and graupel should remain near 0. But in rain, you're going to get appreciable KDP. And then especially in melting hail and graupel, you can have some pretty prolific KDP values. So if we look at each of these terms separately, the precipitation loading term, we know that KDP is well correlated with the liquid water content, which sort of motivates its use for QPE applications. So based on this, there's an argument at least once appreciable melting has occurred that the KDP might be proportional to the precipitation loading. And then as far as the negative thermal buoyancy is concerned, for melting anyway, the increase in liquid water content during melting obviously causes the cooling, but that increase in liquid water content should also increase KDP. So the argument could be made that the rate of change of KDP might be proportional to the cooling rate. And because the hail and graupel is falling, this will manifest as a vertical gradient of KDP. So there's a few caveats. This is sort of an oversimplified conceptual model in motivation. This is strictly only true following a single population of particles. We're kind of treating this like you have a single hailstone falling and melting and what would happen to it. Obviously, in reality, there's size sorting and all sorts of mixing going on. The KDP of melting hail and graupel is going to depend a lot on the distribution of the meltwater, any sort of meltwater shedding you're getting, things of that nature. And then probably the biggest caveat is that evaporation is also a cooling process and will generate negative thermal buoyancy, but it will reduce your KDP, and so have an opposite tendency sign. We don't think that's too big of an issue because in the layer near the wet bulb zero height, where a lot of your graupel melting and cooling is going to be occurring, usually we're not substantially subsaturated, and the more precipitation loading and the more melting you get, that then increases your evaporative potential. Another benefit to using KDP more in a straightforward sense is that a lot of times with descending reflectivity cores, if you have a broad area of enhanced reflectivity, visually it can be a little bit more challenging to identify an enhanced region of Z that's descending, whereas with KDP it's often very visually well defined and identifiable. And as opposed to KDP being well correlated with liquid water content, in the presence of hail, Z is really only going to be a strong function of the largest hailstones you have in your volume. And so for that reason, we think KDP could serve as a very complementary tool to existing downburst signatures. And so to that end, over the past few years, a lot of forecasters have begun to observe and report KDP enhancements that precede downbursts and have begun to incorporate these signatures into their warning decision process. And so the two primary questions our work is really posing is, how ubiquitous are these KDP cores, and specifically in low shear downburst environments? And then is there a correlation between the characteristics of these KDP cores and the intensity of the subsequent downburst? So with that, I'm going to pass over to Charles, who's going to be able to show more about the methodology and results of what he found.
All right, thank you, Jake. I hope everyone can see my PowerPoint. But to address those questions that Jake just mentioned, our goal really is to look at a bunch of different radar data and see if KDP cores might be a quote-unquote good downburst precursor signature. So for the radar analysis, we looked at 81 different downbursts and 2 null events across 24 different cases. There's right about 700 volume scans in total that we looked at. These cases occurred across 10 different states, anywhere from Florida to Arizona, and then up to states like Ohio as well. All of these were warm season events, so between June and August. And all of the events were wet downbursts. So we didn't look at any, well, we tried to look at dry downbursts in Colorado, but there basically weren't any KDP cores with them. So focused on wet downbursts in weak shear environments. And for all of those events, all the volume scans, we measured the median, max, and size of the KDP core. You can see an example of a KDP core over here on the right. And we defined our KDP core as any value of KDP greater than 1 degree per kilometer. And then we measured the evolution of the KDP cores from basically 30 minutes prior to when the downburst developed through the time of downburst max intensity, which we defined as when the maximum 0.5 degree radial velocity occurred. So I'm going to kind of hit you with the 3 big conclusions to start with, and then we'll dive into a little bit more details of each of those conclusions. So through our analysis, we think that KDP cores are a relatively reliable downburst precursor signature. What that means is if there's a KDP core, there's probably going to be a downburst in the next 10 to 20 minutes. Now the strength of of that downburst is a separate challenge, but it is possible that vertical gradients of KDP could provide some more information about that potential intensity, with stronger gradients most of the time being associated with a stronger downburst. Then lastly, and not surprising, environment is important. We have found that it looks like you need a more robust or a stronger KDP core for a downburst to occur if the environment is less favorable for downburst development in the first place. So looking through each of these conclusions, in terms of it being a reliable precursor signature, all 81 downbursts that we looked at were associated with a KDP core. And when I say that, it just means that there was somewhere 1 degree per kilometer or greater KDP near the melting layer. And then in looking at all of these 24 different cases, we were only able to find 2 instances of a KDP core that was not associated with any kind of divergent signature at the surface. And those 2 null KDP cores were very short-lived and very weak. Now, one caveat to that is we were only looking at events and days where the environment was at least somewhat supportive of strong downdrafts and downbursts. It's quite likely that there would be more nulls, which basically just means a KDP core without a divergent signature in a less or unfavorable environment for downbursts. And this really just reinforces the conclusion that environment is important, as with many other things. So why do we say it's a reliable precursor signature? Not only did we see it with every downburst, but there were consistent patterns of KDP evolution near the melting layer prior to many of our downbursts. So this blue line is just showing the evolution of the max KDP over time. The little X here is just showing when the downburst began, and the little O is showing the downburst max intensity time. So this is just a snapshot of 4 different downbursts, and we see this nice pattern of increasing KDP prior to the downburst development, and then it decreases with time as you approach the downburst max intensity. So just 4 events, what does it look like over all 81 downbursts? Well, we averaged all of those maximum values for every downburst, and so the pattern is a little bit more muted, but in general, you can still see an increasing trend in the KDP prior to the downburst max intensity, which would occur at 0 here, and then it would be decreasing after that peak as you approach the downburst max intensity. Same plot, but now we're looking at time prior to downburst development, and we see a nice general increasing trend for the most part prior to the downburst development. So KDP is increasing at the melting layer before the downburst develops. We can also look at lag correlations. So this is basically just showing us that if you have a positive correlation prior to 0, it just means that the KDP core max at the melting layer is increasing prior to the 0.5 degree base velocity increasing. And our most significant correlation occurred at a lead time, if you will, of 3 volume scans. So basically this just means if you see increasing KDP near the melting layer, in about 3 volume scans or so, you could expect there to be increasing base velocity or a strengthening downburst. So if you see a KDP core, it's likely that there's going to be a downburst, but how strong it might be is a bit more challenging. So this is just a violin plot that shows the distribution of maximum KDP near the melting layer for strong downbursts and for weak downbursts. And you can see that there is a lot of overlap in these values. Some of the stronger values do tend to be more associated with strong downbursts rather than weak, but lots of overlap. It could be hard to say, oh, I see a KDP core, and yes, the downburst is going to be severe or impactful, however we want to define that. Now, it is possible that vertical gradients could provide some insight about what that potential intensity could be. So these are just numerical simulations that Jake has run that shows what the vertical profile of KDP might look like. And then, as he mentioned, kind of connecting the change in KDP being associated with a cooling within the downdraft. So if you have more cooling, you'd expect the downdraft to be stronger and maybe expect a stronger downburst as well from that. So we compared the numerical simulations of KDP vertical gradient to the radar observations. So this is looking at all 81 downbursts. What does the KDP look like in the vertical? And we see a pretty similar pattern where it increases below the melting layer as we might expect with melting. And we probably reach some maximum where either melting has ended and we're starting evaporation or other processes are occurring. So it looks pretty similar to what we saw with the simulations, and that is encouraging. And so then we decided to plot out some violin plots just to see if there were differences between strong and weak downbursts. And we found that if you make some assumptions, there is less overlap here than if you just look at KDP near the melting layer. So for this particular one, we assumed that KDP was 0 at the elevation angle nearest the melting layer. And then we calculated what the vertical gradient was from there down to 3 kilometers below the melting layer. And there's still a fair amount of overlap, but there is less. So we see that stronger or larger gradients of KDP in the vertical are more likely to be associated with a strong downburst than a weak one. Also, when we look at something like mature KDP cores, basically just the middle 50% of volume scans, when a KDP core is probably not intensifying or weakening. And if we look at the size of that, so this is showing size, the change in the size of the core in the vertical, we once again see a little less overlap and a little bit more likelihood that a larger change in the size of KDP, of the KDP core with height, could be associated with a stronger downburst rather than a weaker one. And this is relatively new, basically just comparing the vertical profile of strong downbursts versus weak downbursts. The red line is the weak downburst, the black line is the strong downbursts. Once again, all of them, all 81 downbursts, and they do look different. So there could be some differences in just what the vertical profile looks like for KDP for strong and weak downbursts. At the very least, a lower magnitude for those weaker downbursts in terms of KDP at every height, as well as how the gradient or how it changes, how that profile changes with height. And then lastly, environment is important. We have noted that it looks like there needs to be a stronger KDP core in order to get a downburst or a strong downburst if the environment is less favorable for downburst. So here we basically just broke out environments based on downdraft CAPE and a threshold of 1200 joules per kilogram. So you can see that if you have less than 1200 joules per kilogram of DCAPE, the KDP within the KDP core at the melting layer tended to be significantly higher than that when you had strong downdraft CAPE or greater than 1200 joules per kilogram. And same thing if we look at low-level lapse rates. If you have weaker low-level lapse rates, we found stronger KDP cores in those situations. And even when you break it out, we basically decomposed and looked at strong and weak downbursts when you had higher DCAPE and strong and weak downbursts when you had weaker DCAPE. And not only did we find that there was a little bit more difference between the strong and the weak downbursts, but you can also see that in the weak DCAPE, the KDP associated with a strong downburst, the median value is much higher than what we see when there's higher DCAPE. And with the weak downbursts, the KDP median is much higher than what we saw with weak downbursts for in the stronger DCAPE environment. So this could be a way to more or less triage the storms. And you're in a similar environment, you see a stronger KDP core, you might be able to have more confidence that that storm is going to not only produce a downburst, but perhaps produce a stronger downburst as well. So just kind of a quick example on that. In the Birmingham area back in 2018, this was actually one of the less favorable environments that we looked at. So DCAPE was 740 joules per kilogram, low-level lapse rate 7.46 degrees per kilometer, and this was on the low end of the environments that we looked at. There were 3 downbursts, and all 3 of those that are indicated by the black lines had some of the stronger KDP cores that we were looking at. So I think this just reinforces the idea that if you have less favorable conditions for a downburst, you'll probably need to see higher values of KDP near the melting layer to get the same magnitude downburst as you would in a strong or in an environment where conditions are favorable for downbursts. So with that, I'm going to send it over to Randy, who has a lot of case examples for us to look at.
Okay, thanks, Charles. Hopefully you can see my screen. Let's see here. All right, looks like it's showing pretty well. This first loop here kind of indicates this challenge that we were talking about. Obviously, it's these quiescent flow regimes where we're dealing with not a lot of shear at all. And you can see these outflow boundaries here, pretty symmetrical. So it's pretty obvious this case near Nashville, Tennessee was an example of one of these challenges that we're trying to add a little bit of science to, that we can have a little more confidence for our warning forecasters. I think that's important. You know, thinking back to what Tim was presenting earlier, if your warning forecasters have more solid science to really latch onto and can be more comfortable with the environment and the signatures that they're seeing, obviously that's really important to being able to provide the best service possible. So let me just back up just real quick and talk about way back in my days in Goodland, Kansas, talking with Jeremy Martin up there, the Sioux. We were kind of looking at these cases and saying, well, what is there something that we can latch onto? And we think that obviously water loading in the mid levels is a big driver for these events, but what product maybe within dual-pol can help us out? And immediately I think what came to our minds was KDP. So, and then fast forwarding a couple more years after that, you know, by this time, let's see here, let me see if I can advance. There we go. Yeah, by this time I'm in Norman,
Randy.
and this, yeah.
This is Randy Graham. We're seeing your screen in presenter mode,
Okay, sorry about that.
not full screen.
Okay, you should
Still
see
looks
it.
fine, but there we go. Thank you.
Okay. All right, appreciate that, Randy. Sorry about that. Fast forwarding a little bit to Norman, obviously, this is an interesting case. If you look in the middle part of the screen here, you can see the divergent signature is pretty pronounced at the half-degree elevation. Strong inbounds and some outbounds as well. And then you can see the line where I drew a cross section here. I'll show that in just a second, but just showing the environment, there's really not much wind outside of the 10-knot ring on a hodograph there. So it's one of those quiescent environments as far as a flow pattern, just not much at all. And if let me go forward here to the next one, and you'll see that that this was a good example of how you start to see some pretty high KDP aloft, even above or near the freezing level, and then as it descends down, it really picks up in magnitude close to and just below the freezing level, similar to what Charles was talking about, the conceptual model with that. And then it continues to sort of descend, and right about here is where you start to see that significant divergent signature that we showed in the previous slide there. So this is just one example, obviously, but I've learned a lot, obviously, about the microphysics of thunderstorms, and it's been a really amazing opportunity to work with Charles and Jake on this project. And so, you know, obviously, like I said, I think it really helps out to understand the deeper science behind this so that we can enhance our service that we provide. So let me fast forward back to where I started with a slide where I showed the Nashville example. This was an interesting day where there were multiple downbursts, and several of these cases we included within the data set. But this is another example of there's just not much shear at all. And, you know, here's the environment, a lot of instability, obviously, with this. But you can see the winds are fairly weak. There's maybe just a little bit of flow in the mid-levels here. I won't get too deep into the environment other than to say that it really is important, obviously, to know the thermodynamic and kinematic environment with these cases. And here's one event that occurred within several storms that developed that day. And this is on the southwest side of Nashville. You can see that originally there's some pretty high KDP values that descends pretty quickly. Now, obviously you can see it in the reflectivity as well, but I think Charles and Jake kind of mentioned too that there's times where sometimes you have a lot of graupel and hail, and that basically your entire column within a thunderstorm is sort of has a lot of really high reflectivity, and it can be really hard to pick this out. So sometimes the KDP can separate that out a little bit better, and that's one of the first things we noticed. I think the case that Jeremy and I up in Goodland, when we looked at one of our initial cases back in 2014, that was certainly the case where there was a lot of hail within the storm, but the KDP was a little more distinct within the larger, deeper column of higher reflectivity. So it was able to kind of separate that out a little bit. And I think that's maybe an important part of using this technique. So just to kind of fast forward to a couple other events, again, this was just within an hour, another event occurred over downtown Nashville, and you can see that obviously you're not going to get a lot of lead time with this, as Charles mentioned. But if nothing else, what it tells you is that it gives you confidence that if you're otherwise on the fence with the environment and the radar signature, that you see this, and yeah, you may not get a lot of lead time with it, but certainly these really high KDP values, is sort of one of the last scans here before it collapses and hits the ground, is a pretty good indication that you're going to see downburst. Now, again, the magnitude is somewhat in question, but it's also a case where you may not catch this one, but this is telling you something about the environment. It's filling in the gaps that maybe you don't know from your environmental analysis. If you're getting really high KDP like this, that's just below the freezing level and is descending, then that tells you that you certainly have a favorable environment. So if you don't catch this one with much lead time, then it sort of helps you anticipate more of the next one, maybe that you are in a better environment for these downburst type events than you originally anticipated. So that's one way that you can possibly look at it, as a way that it's telling you what the environment is supportive of or is capable of. And here's another case. Again, this is a little more clear. There's ZDR as well, which, the main focus obviously for this presentation is the KDP, but you can see the reflectivity core descending. But along with that, when this loops back through, you can see that the KDP core becomes quite substantial near the freezing level and then descends to the ground. And another downburst occurred with this. Now, this was another case that occurred in Birmingham. And then here's, going back to the Nashville case, here's another event too that sort of shows it from more of a low-level reflectivity and low-level KDP perspective instead of a cross-section. What's interesting here is that a lot of times you see these divergent signatures are coincident with the higher KDP values. Thought that was really interesting. Again, it sort of fits the conceptual model. When these higher KDP values hit the ground, then they sort of manifest into a downburst or a divergent signature. And again, with this, not a lot of lead time, but at least it tells you that it connects the dots and fills in the gaps with your conceptual model. Here's another example of that too. You can see a pretty substantial divergent signature here. Southwest of Nashville, that one case we showed earlier with a cross section, and you notice the KDP becomes quite large at the time that occurs. And yet another example too from one of the cases that Charles showed earlier. You can see the LSR icons for the wind reports that occur with this. A couple somewhat subtle or divergent signatures that you see in the velocity on the right, and then the KDP cores that sort of pop up right about that time. You can see one here and a couple of them. There's about 3 events or so, and then with time the LSR start to come in that there was some tree damage with that too. So those are just some examples, and just again to reemphasize that when you couple this with environmental information and some of the legacy radar techniques that we're used to using, such as reflectivity, suspended cores aloft, that it can give you more confidence as to what the situation sort of is ongoing now or how it's evolving. I think that's a really important part of this. Had a good conversation with Dustin Jordan over in Jackson, Kentucky, and he talked about maybe that this would sort of fit this concept of what we use for QLCS mesovortex detection. Jason Shaman et al., they kind of looked at the confidence builders and nudgers. Well, it's maybe the same concept could be applied with the KDP cores. Again, it may not solve the entire problem, and it's not a guarantee that you're going to have a downburst with 30 minutes lead time every time. Obviously, that's not the case, but it certainly is another tool for us to be able to add to the environmental analysis and the radar analysis to help us anticipate these events. And so with that, I guess I will turn it back over to Charles for some final words.
Thanks, Randy. Those are all really interesting cases and thoughts, and we really appreciate you being so involved with this research. I think it's really important to keep all research efforts as focused operationally as possible, and so your input has been very, very valuable. And of course, we always look for input from anybody listening on this call. We're always interested in your thoughts about the work that we're showing, your thoughts about any radar signature. If there's something you're like, I wonder, what might this look like with a large statistical analysis or something like that. That's the kind of stuff we're always interested in, because we want to make sure that the research we do is usable and useful ultimately in terms of warning the public or IDSS situations about impactful weather. So just to quickly summarize everything, some of our work here does suggest that KDP cores could be an effective and reliable downburst precursor signature, just because they have, or at least in our cases, we have observed them to precede downburst development and max intensity. And it makes sense with the conceptual model of water loading and melting that Jake presented early in the presentation. As with many other things, the environment is important to consider along with radar. Randy was mentioning the kind of confidence builders and nudgers approach that the 3 ingredients method takes on, and that can include environmental variables as well as what you see in the radar. We have more work to be done in terms of looking at those vertical gradients and how those might be useful. Those are especially challenging because that's going to be something that's difficult to calculate, difficult to see in a real-time warning situation than would be, say, max KDP at a certain level. But at the very least, like I've mentioned, that looking at maximum KDP near the melting layer does appear to at least say, yeah, there's going to be a downburst, and we just have more work to do to see if we can suss out exactly how strong that downburst might be. One thing we didn't talk about much was that these KDP cores do evolve relatively slowly, quote unquote, as in, as much as 3 to 4 to 5 volume scans, 5-minute, volume scans, which means that it can be sampled multiple times by the 88D network. Some of the other signatures that I've looked at in downbursts, some of them evolve really, really quickly, like 10 minutes or less, such as mid-level convergence can evolve really quickly, so can descending reflectivity cores in certain situations. So it's possible that this signature will be a little easier to see because of its slower evolution time. And we think that might be just because melting is present near the melting layer for a long duration of time. Even after the initial nose of the downburst, if you will, is descended below it, there are still melting particles within the downdraft that would be seen as high KDP near the melting layer. Now, some of the limitations we did encounter was what is the true intensity of a downburst. So we're all familiar with the limitations in storm data. We're all familiar with radar limitations about how exactly is the base velocity, is it an exact representation of how strong a given downburst actually is. So in all of the results that I showed, strong and weak downbursts were determined using a combination of storm reports and base velocity measurements, but we just can't say for sure how strong or weak a downburst is. So correlating the KDP core magnitude with downburst intensity has been challenging. KDP can be a little messy, a little noisy sometimes, especially when the reflectivity is lower. And then our sample size. We had 81 downbursts, which is pretty good size, but that can always be increased. And then there were no cases from days where we weren't looking for downbursts. So we didn't look at weak convection in an environment where the low-level lapse rates were really low. And so it's possible that there are more nulls in that day. But hopefully you wouldn't be thinking about or really be expecting strong downbursts if the environment suggests there won't be any. But something to consider. And then there are lots of different things that go into making a downdraft strong, and what the outflow pattern at the surface actually looks like and how it's measured. So I think this is a challenge for a reason, but we're pretty hopeful that KDP cores can provide more information and maybe an important piece for the downburst conceptual model. So with that, thank you everybody for listening, and we will open it up for any questions if anybody has any.